All right, let's start. So today, we're just going to do a continuation of last week where we talked about electrostatics, and today we're going to be moving on to circuits. We talked a bit about them last time, and I'll just go over it again here. I kind of rushed through it last time, so basically, we're just going to go review again about the circuits, the analogy that goes with like the river and stuff, and we'll talk more about circuits and other functions of it. So to begin with, you can think of a circuit as kind of a river or like a waterfall. So basically, in this kind of pseudo analogy, voltage, which is a term that applies to current to circuits, basically voltage is equivalent to the way a height difference causes water to flow down some kind of river or waterfall. And you can think of it as like the driving force, or you can think of gravity, I guess, as a driving force, because gravity is what allows you to make use of the heights and will accelerate water towards the ground. Just like that, voltage will cause electrons to flow through a wire. And resistance, basically the same thing as we can call it resistance of a river. It's like rocks and debris, stuff like that. They won't let water flow through. So you can think of the same thing as for resistance. Basically resistance, the higher the resistance, the more difficult it is for electrons to flow through a wire. And current is just like the main kind of property of some kind of circuit, where it's how quickly the electrons are flowing through the circuit. So, or I guess how great the flow is. So in this case, very similar to the idea of a river, where current is just like a river's current, where water is flowing through a river, current is electrons flowing through a wire. And we can combine all three of these terms, all three of these variables, with Ohm's law. So this is Mr. Ohm, and I is equal to VR is his equation, and I stands for current, V stands for voltage, and R stands for resistance. So we can see here how, let's say for some kind of theoretical example, let's say I have some kind of circuit, and let's say I increase the voltage of it. So if I increase the voltage of it while keeping resistance the same, you don't have to know like how I'm doing this, for instance, but we'll get to that. And for now, we'll just talk about these variables on a larger scope. If you can see, if I increase the V, and let's say the resistance, let's say the circuit stays the same, so the resistance will stay the same, then we'll just say like R will just be equal, V will increase. That means that according to this equation, if R is the same and V increases, then I will also increase as a result. And this kind of follows our analogy, because we can think of the voltage as the difference in height, and then the steeper some kind of slope is, the more quickly water will flow down that slope. So just like that, the more quickly electrons will flow through a wire. Similarly, if I do something like increase, or let's say decrease the resistance while still increasing the voltage, and you can see that decreasing the denominator here, because it's V over R, then if I decrease the resistance, well, actually I'll just keep voltage the same. So this will just be equal still. So V won't change, but if I decrease the resistance, then that means there's less things to impede like a river flowing down. So then it'll be easier for it to flow. So that means the current will increase. So from this equation, we can see that indeed current does increase. And you can do this with any number of ways. You can say increase the current. Well, then what would we expect to see in change in voltage or change in resistance, depending on which of those changes. So we can use this kind of equation to predict things based on this rule of proportionality. All right. So basically, for circuits, you've probably seen this kind of diagram before, or like seen some kind of way in which electrons are able to flow through a wire. But basically, if a circuit is open, then there's a hole in it, and electrons can't flow through. If it's a closed circuit, then electrons are able to flow through, and then that allows for everything to work, allows for basically this river to keep flowing. And this is kind of where the river analogy breaks down, because obviously, if you had only part of a river, if it didn't flow into itself, it would obviously still flow just because of gravity. It does not work like that for circuits. It's just you need to have a closed circuit in order for the electrons to flow through. If it's not connected, then it's basically this battery won't be able to do anything. So these are what we call circuit elements, basically the things that go on in a circuit. So if you saw over here, each of these different drawings here, each of these different symbols is some kind of element. So for instance, this thing is a battery. This thing is obviously a light bulb, which is a drawing. And all this line through the entire circuit is the wire. So it's summed up for you here. This is the way that like you might see this in books and stuff, where you'll see a cell, a battery like this, a lamp could be like this. You might also see it drawn like this. A switch, pretty self-explanatory. You just, if it's open like this, then that means the wire is here. This is the wire. These are two wires, and this is an open switch. If you wanted to draw a closed switch, you could do something like this, where you just have it closed, and that way the wire is allowed to connect and the current will flow through. And wires are obviously just like the lines. And for resistors, very similar to the idea of a lamp, you can think of the lamp as a resistor basically, and you can think of it as like taking part of the energy that's coming from the, I guess, the power cell, the battery, like from throughout this entire circuit. It's basically draining some of that power to light the light bulb. And if you prefer to not have a light bulb, if you just want some kind of resistance, then some standard drawings are either this kind of this rectangle thing, and you can like write like, let's say 5 ohms. This is capital omega here, and it's a symbol for an ohm as unit of resistance. You can also draw it like this as resistor, kind of like that spike, this kind of spiky line here. That's also a symbol for resistor. So a bunch of different things you can do with that. And yeah, these are like the basic circuit elements you will see. And for current and voltage, as we just mentioned, just to remind you, current is I, and according to Ohm's law, I is equal to V over R. So V is voltage and R is resistance. And resistance is pretty standard to measure. You just basically figure out the resistance of an object. You can find that through Ohm's law by measuring other things, but generally you just like see a resistor and its manufacturer label or something will just tell you the resistance. But measuring current and voltage difference can be a bit more tricky. Basically, there is a process that goes into these, and the way ammeters work is you measure current. So you might see current like, well, you might see a circuit like this. Let's say, just draw a simple one right here. This is going to be a small resistor, and this is going to be a closed circuit. So just a battery and a resistor, nothing too fancy here. What I'm going to do is I'm actually going to draw an ammeter here. The way you would connect an ammeter is you would put it in the same line as the wire. So you basically just insert the ammeter into where the current's flowing. So I'll just do this a different color. Right now, let's say the current's flowing from here to here. The big side of the battery is where the current comes out of. That's just the convention of it. It doesn't really matter what direction or like how one draws this, but because of convention, scientists have decided like years ago, hundreds of years ago, that like, hey, this is the way we're going to draw this battery. So the battery positive side will be this one, and the negative side will be this one. So this is how you should always be drawing batteries. And yeah, this is the way current flows. So basically you just slap on an ammeter right here in the middle of the current. I guess the current would be flowing more like this, right through the wires, and current's in this direction. So you just put an ammeter right in the middle of that wire, and then the ammeter will spit out the value of whatever current is going through it. I'm not going to get into how an ammeter works, but it basically is just a small circuit inside of it that is able to measure the current. Conversely, if I draw this, if I can, wrong color. For anyone just joining, basically we're just talking about circuits again. We reviewed a bit of it before in the previous few slides that we already saw last week. Basically, you have your standard river analogy of just the idea of, I'll clear it all for now. Basically, voltage is the difference in height, basically, of a river, the steepness of a river. So the greater the voltage, the greater the current, the greater, like basically how quickly the electrons / water moves in analogy. Resistance is just like the rocks, debris that could impede the current. So the greater the resistance, the lower the current. And current is just this idea of how quickly something is moving through that medium. So either it's the water flowing through a river, it's electrons flowing through a circuit in the case of electricity and magnetism. So yeah, that's current. And then Ohm's law combines all three of them with this very succinct equation. Very beautiful. And you can see basically all of the different kinds of properties that we talked about, like voltage. If you increase the steepness of it, as opposed to like if it's less steep or more steep, then more steepness means water flows faster. So more voltage means current is greater. So you can see that they're proportional, whereas resistance is inversely proportional to current because it's over R. And you can think of it as like if you have some kind of river, increase the resistance, then basically you're like putting more rocks in it, putting some debris in it. It impedes the flow of the water, so you're decreasing the current. So if you increase R, you can see that in this equation, I will decrease, assuming V stays constant. So that's just a quick review of Ohm's law. Circuits, in order for electrons to properly flow, circuit has to be closed. And these are different circuit elements you can see here. This is like how I would hand draw these. And yeah, cell is just a battery. And lamp is basically just a resistor. You can draw any kind of resistor you want. So this is one possible drawing for resistor. You could draw like either of these two ways as well. Doesn't really matter as long as you know what you're talking about. And yeah, so now we're talking about how to measure currents and voltages. So we're talking about currents, and I'll just redraw my quick little sketch here of a circuit diagram. A small resistor there, and this is going to be our circuit. So the way voltage voltmeter works is it has to measure a voltage difference, because you can't just measure a voltage and say, okay, that's the voltage. You can't just say like, okay, this spot is 6 volts. You would have to say in comparison to what? Just like how if you wanted to say, hey, the top of that hill is 5 meters high, right? It doesn't really make sense to say 5 meters high. You have to say 5 meters high from where I'm standing, or 5 meters high from that other hill, so something like that. You have to give some kind of reference point, and you have to compare two things in order to make sense of a height difference. So for instance, you might say like sea level would be 0 altitude. That's the standard height we would use. So if you say like, oh, that mountain's like X kilometers, or the peak of the mountain has an altitude of X kilometers, you would know like that's X kilometers from sea level. So we already have that kind of difference idea already baked into the idea of altitude. And we have to do something similar to this, where, or actually we don't have anything similar to this because there's no really 0 voltage. So you have to think of it as a voltage difference instead. So if you measured, say, this point here and measure this point here, let's say you want to measure the voltage difference between those 2 points, you would put a voltmeter right here. And basically what this voltmeter does is it just puts it right here in parallel with the circuit. I'll talk more about series and parallel later. Basically, this means you put it on the side of it. So remember, an ammeter, we just had it right through the circuit like this. Voltmeter, you would have to put it on the side of it. So if I want to put it here, I could put it like here, branching off from the circuit. And then that'd be a proper way to place a voltmeter. And there's a problem with the way I placed it right now, because effectively, assuming we have ideal wires means that they are perfectly conducting, they have 0 resistance, then the voltage difference between these 2 points, this one and this one, should be 0. And why is that? That's because if you remember Ohm's law, we have I equals V over R. Some algebra tells us that V is equal to IR. So if we wanted to measure the voltage difference between 2 points, we would measure the current, the I, times the resistance, the R. And you can see here, there is some amount of current. We don't know what it is because we haven't said what the resistance is. We haven't said what the current is, so we don't know that. However, we can say it's, let's say, some positive value, right? Assuming the battery isn't out of the juice, we can say that there is some positive value of current. But the problem here is that resistance is going to be 0 because these wires, as we assumed, are ideal. So if you were in the real world and you put a voltmeter between 2 wires like this, you'd probably still get a reading very, very close to 0. It wouldn't exactly be 0 because all things have to have some amount of resistance unless it's made like super well made in the laboratory and stuff, called a superconductor. But for all of our purposes, you're never going to find a perfect conductor in the real world. And in this case, we are assuming that we have a perfect conductor. So that means that resistance is 0. So the voltage difference here would be 0. So you might write voltage difference as delta V. This is the Greek letter delta. It's just a small triangle, and it means change in. So change in V is equal to IR. And IR is 0. So changing V is 0. The voltage difference between these 2 points is 0. So this voltmeter will give us a reading of 0. So, oh, I should have done that. I'll just clear this part. I'll clear this as well, I guess. So I'll redraw this part of the circuit. And now we want to know, like, what would be a place that we could put this voltmeter, I'm assuming over there, to find something that's actually useful. How can we use a voltmeter that's actually going to give us a normal reading that's not just something stupid like 0? We could put something here, for instance, want to measure between this point and this point, because then we would have a resistance in between, a positive resistance, and that would tell us the voltage difference. So we could slap it right there. That's our voltmeter. And then, according to Ohm's law again, we have V equals IR. So I is some unknown number, is positive, as is R, because now we know that R is just this R, because it has these wires, which contribute 0 resistance, because we're assuming they're ideal, and we have this resistor, which is R. So that means that the voltage reading here would be equal to IR, whatever that value is. We don't really care right now, but we know it'll be equal to that value. Similarly, we can also do something like this, where we put a voltage or voltmeter to measure the voltage right here. And this is across a battery. And a battery always gives the same voltage. That is what we're assuming. Obviously, in the real world, batteries decay over time. They won't work as well over time. So they'll lose some of their voltage and eventually go out. But we're assuming that this battery will always provide the same constant voltage. And we'll call that V0, let's say. So this is going to be V0. So this voltmeter will simply measure the difference in voltage. And what's the difference in voltage? Is the voltage difference that the battery provides. So V will be measured as V0, which makes a lot of sense. And you might notice here that both of these points basically correspond because they are both connected by a wire and just a wire, which means that if you measure the voltage difference between them, as we showed here before, like between these 2 points have a voltage difference of 0. So similarly, we could say the voltage difference between here and here is 0. So we can basically combine these 2 points. I'll just do something like this. Oops, took about a bit too much. We could instead measure the voltage difference from here and here, right? And then basically that's the same as measuring also, because these 2 points, this one, I'll use a different color for this actually. Oops. This one and this one, right? These 2 points, just like the other 2 points, just like the point over here and the one that used to be over here, they're the same because they're connected by a wire. So theoretically, we could also just like collapse this wire, and you could think of it as, oops, this voltmeter. Oops, that's the wrong color. This voltmeter is measuring the difference in voltage between this and this. So these 2 points, which is the same as the voltmeter from before. So these 2 voltmeters are actually measuring the same thing, which might be surprising because for one of them, we got V0, the other one we got IR. And you might try to figure out like, how is this possible? Because those seem like different values. But according to Ohm's law tells us that in fact, V equals IR. So we can compare the two. Well, V0 is the V0 here, and IR is simply the IR from this value. So V0 does in fact equal IR, which tells us that this is true. These 2 voltmeters were actually measuring the same thing. It's just that we measured them across different circuit elements. So you can do that. You can basically, if you want to measure the voltage difference between 2 different points, you could look at this one and this one and say, oh, I want to find the difference between those points. And you could look at the voltage between here or between all the way around here. And it's up to you to decide which one's easier in many circumstances. In this case, you could probably say that this one, in fact, the one that might be less intuitive because it's longer, the one over here might be easier because you're just measuring it across a battery and you already know the voltage of that battery. So rather than having to calculate like, oh, V equals IR, plug in IR equals V0 from this equation over here, from Ohm's law again, you can just go directly to V equals V0. That diagram's pretty messy. You get the picture. Any questions about this? like any circuit questions, voltage, currents, resistance, any of that. All right, if there are not any, I will move on. So here is, oops, look at that. I'll send this link in chat. Go. I'll click on lab. So this is just a simulation that lets you basically build whatever circuit you want. So there's wires, there's a battery, there's like light bulb. Light bulb is basically just resistor. Also like an actual resistor. There's a switch here. There's a bunch of other stuff. Lots of different things you can use. Some maybe morbid things you can use. But yeah, there's wires. Each of these red circles means you can connect two things. So if I want to connect to a battery, to a wire, I would just put these two circles together. They form a black circle. That means there's a connection there. If I want to unconnect them, I just click on the black circle and hit the cut, and then it'll unconnect. So I'll put it back on. I'll put it next to this wire. And let's say I want to light this light bulb. So I'll put on some wire here. And notice, obviously, electrons aren't flowing because it's not a connected circuit yet. What I'll do is I shall connect it, and it'll start flowing. Current will start flowing, the light bulb will light up normally, and all is well. So well, let's put these two elements back, and you can see here that this is working, and I can change a lot of things. So I can change the voltage of the battery, I can change the resistance of the light bulb, and using these two different things, I can change the current. So current, you can see basically represented by the electrons here. You can see that it's a decent pace, and if I want to increase it, there are actually two ways I can use these two elements here to increase it. So remember, we have Ohm's law that states I equals V over. So one way I can try to manipulate current here, because I don't have like a button that can just say increase current or decrease current, but I can use V and R to change them. So if I want to increase I, one thing I can do is I can increase V while keeping R the same. So if I increase V, use a slider, you'll see that electrons will flow much faster and light will become much brighter. And let's say I wanted to decrease I. Now I think it's too bright. Now I think electrons are flowing too fast. Let's say I want to decrease it. Well, I can do that either by turning down the voltage. I can decrease it a bit. But let's say I think it's still too bright. I don't want to decrease the voltage anymore. Then another tool I have at my disposal here is to increase R. Because if I increase R on the bottom here, on the denominator, I will decrease. So I can increase R, and you can see, as expected, the current slows way down. Wow, the bulb also shines less brightly. So back to low resistance, and it's flowing pretty quickly. And then high resistance almost comes to a halt. If I pump it all the way there, you can see that electrons are now like barely moving. Electron is the light bulb is very dim, and you can see how everything is like this. I can also use a current, an ammeter, to find the current. The way this one works isn't the one you would normally see in a lab. This one is just like a quick simulation kind of current meter, ammeter. So I'll move it back to like a more normal value, I guess. And I can just hover over wherever I want with this current. You can see here it's 0.77 amps all the way around, because current will be constant through a singular branch. Because if, say, the current here at this point were larger than this point, it would cause a weird buildup of charges, which wouldn't really make sense in a wire. Because if charges were to build up somewhere, let's say here it was like 1 amp and here it was 0.5 amps, that would mean that going into this wire over here, there'd be 1 amp going in and half an amp going out, right? Well, let's say, actually, let's make the numbers nicer. 2 amps going in, 1 amp going out, which would mean that there would be a net 1 amp into this wire here, which means charge would build up. And as charge builds up, then it would be basically kind of also pseudo increasing the resistance, because it'd be harder for electrons to flow into something that's already negatively charged. Because as we saw last week, electrons will push away other electrons because negative particles push away other negative particles. Therefore, any kind of scenario where there's a buildup of charges, where there's a current that isn't the same at all places, will be corrected to become the same at all places, because if there's ever a buildup of charges, then that buildup itself will decrease the amount of current going into the place while increase the current going out, which will mean that eventually all will be well, current will correct itself, and everything will be back to how it should be. So you can see here, as you can see, current is all the same. If I change it to a voltmeter tool, I'll put the current tool back, just slide it into this box over here. And voltage, you can see that there are two kind of these pins. Well, current only had one, because all you have to do is just measure 1 point, plain and simple. Voltmeter, you have to choose 2 points, because as we said, it doesn't make sense to have a voltage without some kind of reference point, some kind of second point to compare it to. So voltage, let's say if I just only put one down, it still doesn't know what's going on because you only have 1 point. If I put them both on the same wire here, it'll be 0.000 volts. And that'll be infinite zeros until infinity, right? Because it's just 0 volts, because there's zero resistance in these wires. If I were instead to change voltmeter to measure between this point on the wire here and this point on the wire here past the light bulb, remember a light bulb is the same basically as a resistor, and you can see that the voltage is now some positive value. It's I times R. And then if I changed it to, let's say here, where we're measuring the change between voltage of the battery, you can see similarly, it's still 23 volts. And no matter where I go in here, it's always going to be 23 volts with this red thing, because as long as I'm on this wire, the resistance won't change. There will be zeros of resistance, which means voltage won't change. So the voltage difference will stay the same. But if I move it past into over here, then voltage will again be 0 because it's on the same wire. And I can do the same thing with this black one. Move it all around. It will always be 23 until I move it back to the same wire. So there's a bunch of other circuit elements. For instance, there's a switch here. I'll cut this for a second, and I'll put a switch in its place. And you can see, as long as the switch is open, the current or the circuit is not connected. But if I close it, by tapping on it, I can change whether it's open or closed, and I can choose if I want it to be open or closed, and therefore whether the circuit is on or off. That's what we call a switch. Also, this button on here just changes everything to the drawing kind of diagram. So there's that. There's some other things here. A bunch of other different, like there's a dog for some reason, a hand, some more rather weird things. But yeah, main things to see here are the light bulb and the switch, the battery, these basic circuit elements that are really constitute the majority of the circuits you'll be working with. Any questions with any of this? The Ohm's law, these circuits, the circuit builder. I guess not. So I will continue with the rest of the slides. And you can, I have to link in chat. So if you want to go back to this simulation, you can feel free to. I'll clear all the drawings. All right. So now we're going to talk a bit more about those branches and putting things in parallel and series, as I said before. So parallel basically means that it doesn't have to be parallel per se. Like if I had a circuit like this, I'll draw it real quick. I had a circuit like this where I had one resistor right here, like this, another one like this. These two branches, this one and this one, obviously aren't parallel because that's not how parallel lines work, but they are still referred to as branches that are in parallel. And that's because you can always manipulate them. You can always just turn this wire a bit like this and make it in parallel. And as long as it's not in series, then this connection is in parallel. So parallel means this. That's just a cleaner way of drawing it, more easy to look at. And basically, the key thing to know about parallel branches is that the voltage difference will be the same. And why is that? Because you can see here, if I measure voltage difference between, let's say, this blue point here and this green point here at the bottom, it would be the same as measuring the difference between this point on the bottom and this blue point at the top. And that's because you can think of it as, using Ohm's law again, if you put a voltmeter right here, what would the voltmeter give you? It would just be 0 because, as we know, wires have 0 resistance. So Ohm's law tells us the voltage difference between these 2 points is 0. So this entire piece here might as well be the same. And for that matter, we can say this entire branch all the way around here all has the same voltage. Likewise, we can use green and we can say the same thing about the bottom half here. So I can draw this green kind of outline and say that all of this will have the same voltage. So if you put a voltmeter around anything from here, like this, anything, voltmeter to anywhere, it will always give you the same reading, which means that these 2 branches will have the same voltage difference. So between here and here, same thing as here and here. And that's very powerful because we can use this in conjunction with Ohm's law to figure out some interesting things. So if we just write this equation, we can call this V1 between these 2 points, V1, V2. So this is V1 equals V2, right? That's just what we showed. And then let's say that this resistor is called R1. This one is called R2, just for keeping things nice and simple. And likewise, we'll have this one just be called I1. This one will be called I2 for the currents in each branch. Notice how the currents aren't the same. They don't have to be the same. They could be the same, but they don't have to be because these 2 branches aren't necessarily symmetric. So right here at this junction, where there's an intersection between the wires coming in, coming out, you can see that the current will have to choose where to go. So there's a split in the current and it'll figure out where it wants to go from there. So I can call this I with no subscript right here, coming from the battery directly. It'll have to choose where it wants to go. So here we have V1 equals V2, and using Ohm's law, we can plug in V1 is equal to I1 times R1. And V2, similarly, is equal to I2 times R2. So what's that tell us? We can figure out some things from there. But in conjunction with that, we will also need to use what we call the junction rule. So I'll use this bigger diagram over here. Junction rule states that once you have any kind of junction, any kind of intersection, for instance, this one right here, you can say that the current going into that junction, this point right here, is equal to the current going out of that junction. So this current I is going into the junction, whereas both of these currents are going out of the junction. So I1 and I2, they're both going out of the junction, and their total magnitudes, their total currents, have to add up to an equal value to this I here. So more succinctly, I can say I is equal to I1 plus I2. And like we talked about before, we can't ever have charge build up on any spot in the wire, because if that were to happen, then it would very quickly correct itself, because if it's more negative than any other spot on the wire, then electrons would be prevented from entering that spot until those electrons kept moving on, and then that'd be basically correcting itself. It's self-correcting. So then we have this kind of rule here. And we don't have to just use this with junction. We can apply it to any kind of point you want. So let's say right here, we can say that the current going into here, that would be I2, but it's on the same branches here, is equal to the current going out. So that's also I2. But obviously that's true, and there's no real need to say that. But just so you know, you can also use this kind of prove, I guess, that the current in one spot is going to be the same coming out of that one spot. So I'll erase all this. I'll keep up the junction rule here. So this is very powerful, and we can use this. I'll just put it down here. I is equal to I1 plus I2. And now I can do some algebra here. So let's say I plug in I1 is equal to, well, I can divide by R1 on both sides. It's going to be equal to R2 over R1 times I2. And I can substitute that into this variable right here to get I is equal to R2 over R1 times I2 plus I2. And what's that give us? Well, what we can do is we can combine these two fractions to get I2 is equal to, or I2 times 1 plus R2 over R1. And if we distribute that, we would get R1 plus R2, just through some algebra. And then what we can see here is we can get, well, basically our goal here is trying to figure out how we can possibly combine these two resistors into just equivalently one resistor. It's obviously still going to be two resistors, but we want to figure out some kind of equivalence ratio we can use with these resistors. So what I'm trying to do here is we can look here and say that this R1 plus R2, actually no, we can see that basically if we want to find some kind of R to figure out, wait, did I do a mistake here? No, I think I'm okay. So if I want to figure out the total R, then basically what I would want to find is that R is equal to the total voltage, right? So V, I'll call it, this calls it V, I'll simply call it V for simplicity's sake. This is RE, R equivalent, which is basically the equivalent resistance of these two. And it's not as simple as just adding up the resistances, though we'll see how it is like that for the case in series. We basically want to figure out some kind of RE such that this is true. So I want to basically figure out that this is going to be equal to V. So I think I did this a bit wrong. Let me just figure out what I did here. All right, yeah. So if I just have to find V, basically, we already knew that this is V, voltage difference. I'm actually going to use this diagram as well. So erasing this part. We saw before that these two branches, this blue branch covered over a bit with some red, but basically this blue branch here has the same voltage difference throughout as opposed to the green branch down here. Which means that if we take this voltage difference between these 2 points here, well, just using red, between this point and this point, it's the same as the rest of these points, right? So this is also still V, which means that basically V is going to be the same for all of these. So this is equal to, let's get rid of this circle here. This is going to be equal to just I1 times R1. We can see if we use I, then I was equal to this expression right over here. So I, if we plug that in, I'll plug that in on this side. So I 2 times, this is 1, R1 plus R2 over R1 is the equation. So this is going to be plugging in for this I right here. We still have RE is equal to I1 times R1. Cutting a bit into this diagram, that's okay. Well, actually, I should use this instead. So this is I2 times R2. So it's equivalent, but we're going to be canceling out these expressions here. So I2 times R2. So then some simple algebra tells us we can cancel out I2, of course, and then we can shift everything over to the right to get RE is equal to R1 times R2 all over R1 plus R2. So this is our expression for R equivalent. Pretty complicated, and you can simplify this expression by basically saying the same as this equation right here. If you just take the reciprocal of this, you can get 1 over RE is equal to R1 plus R2 all over R1 times R2. And then that's going to be equal to this expression right here. I kind of covered it all up by now with these circles, but this expression is algebraically equivalent to this expression. You can just see by expanding it out. If you combine these two equations, these two fractions, you would get this. So this is a rather, I'll actually just clear it all now, or this part here, I guess. This equation is pretty easy to remember, I'd say. It just this nice equation. It's the same thing as R equals R1 plus R2, but just with 1 over on all of them. So not too hard to remember. It's pretty elegant. And basically, you can see from this equation, let's say I have R1 equals 2 ohms, right? So this is, I'll work up here in case you want us to look at the rest of it. So R1 over RE, let's say each resistor was just 2 ohms. So then 1/2 plus 1/2, that's going to be equal to 1. And then RE will equal 1 ohm. So you can basically see, if you just try some values, plug in some values, that RE always has to be less than R1 or R2, or both of them actually, I should say. RE is always going to be less than R1 and R2. And that's because you can think of it as the debris, right? If we go back to our analogy of the debris, you can think of this kind of splitting path as different ways the water can take. And the water doesn't just know. The water already knows, in this scenario of a circuit, the water knows that in front of it are these two resistors. So it'll always try to, well, not always try, but basically it wants to reach the other side. It wants to go from here, from this junction, right, over to here, to the other side. It always wants to keep flowing, just because the battery is pushing it that way. So because of that, we can basically reason that the more options there are for this current from this piece of current here, this piece of charge, this electron, whatever you want to think of it as, to go from point A to point B, if there's more options, it's easier to travel there, because let's say some go this way, some will go that way. That's easier than fitting them all through the same pipeline. So if I got rid of R2 over here, which is only R1, only one spot, all the electrons will go through this one path, and it'll be pretty difficult to get there. But if suddenly I open basically 2 lanes of traffic, it's a second highway or something, then some cars can go here, some cars can go there, some water can go here, some water can go there, right? That means that electrons can go either this direction or that direction, and it'll be therefore easier to get to point B, no matter what the resistances are. Even if this resistor was like 1 ohm and this resistor was like 99 ohms or something, it would still be less than 1 ohm, because no matter how small, or no matter how big, I should say, this resistor is, as long as it provides another option for these electrons to get from point A to point B, then it'll be just that tiny bit easier to get from point A to point B, of course. So that means that the resistance will still decrease, even if it's just by a small amount. So you can try out all the values. You'll see that R equivalent is always going to be less than R1 and R2 both. Hopefully that all makes sense. It's a pretty, I guess, long derivation. But yeah, I think that's a pretty cool equation. Any questions on this derivation? All right, if not, we'll be talking about resistors in series. I think this one's actually a little bit simpler, so it might just take a little bit more stuff to get there. So we don't have to use junction rule or anything, just one series. So these two resistors are what we call in series because they're just right next to each other, they're consecutive, and they're part of the same branch. And because they're part of the same branch, we can see that the current has to be the same throughout the entire thing. So all the way around here, current is going to be the exact same. However, differently from before, we can't say that V is going to be equal to like V1 is equal to V2, because suddenly these two aren't parallel anymore. They're in series now. So we can't just equate V1 and V2. So that means, how do we solve this? What's our equations? Well, now we can say that, let's say this current here, this current through this resistor, let's call that I1, as we did before. This one's going to be called I2. And of course, we can set I1 equals I2. Might seem a little stupid, might seem a little silly to have two different variable names that we already know are equal, but just bear with me. So using Ohm's law again, we can say that I1 is equal to V1 over R1. I'll write that out. And I2 is equal to, similarly, using the same variables, but as different subscripts, V2 over R2, which means we can say that V1 over R1 is equal to V2 over R2. All right, now, just like the way that we had our previous rule for junction rule, if you have one junction, if you have a current go into it, an equal amount of current has to go out of it. You can kind of think that similarly to this next rule called loop rule. What loop rule says, for any loop, the total sum of all the voltage has to be equal to 0. And you might think, well, how does that even make sense? Because the voltage here is VB, let's call it V, between these 2 points. This is going to be V, and this is V1, this is V2. So V is positive, V1 is positive, V2 is positive. The positive numbers, how can I possibly add to 0? Well, the trick here is that V isn't actually positive. It's actually, you can think of it as, or I should say V1 and V2 aren't positive. It really depends on how you're positioning yourself. You can think of it either as going one direction or the other direction, but you can generally we like to assume that V1 and V2 are actually negative, because you can think of it as this VB here, this battery, is providing some amount of voltage V to the circuit. And as it goes through the resistors, each resistor takes away some amount of that voltage. So this one will take away, this resistor takes away some amount of voltage from the circuit. So V1 takes away V1 amounts of voltage, and V2 takes back V2 amount of voltage, which means that eventually it'll come back here and it'll be left with 0 voltage. And then the battery will pump some more voltage into this current, into the circuit, and that way it'll be at V again. It'll start the process all over again. So using the height analogy, I guess you could say, you can think of it maybe as like a person traveling around some kind of hilly region, I guess. So I guess the way I would draw this would be like something like this, where this is some kind of ladder up here. You think of it as a battery. The person is climbing the ladder, and they go up the ladder, and then there's like there's a cliff or something, so they go down the mountain. There's another cliff, and then they go back. So basically, what we're doing here is we're seeing this ladder providing the boost that the climber needs to get up there, and they can go down. So this is like V1, can go down again, V2, and they can go back around. This isn't going down. This part isn't going down. This is just like coming around to the front, or it can go back up the ladder. So not the most well-drawn diagram. Hopefully it makes a little bit of sense. Basically, what we're saying here is that the battery is providing some kind of voltage, and the resistors take it away. The resistors basically use that voltage to turn it into other forms of energy, like thermal energy. Often it's used as heat. You can use this kind of energy in the form of a light bulb, so light energy. Most often, though, it'll be heat, inefficiencies, and stuff like that. So back to our derivation here, we can use loop rule to say that VB, or I'll just say V for simplicity, V total, this V, is equal to V1 plus V2. And with that, we can more easily figure out what we're doing here. So we want to figure out our equivalent. That's our main goal. So our equivalent, RE, times I, and I is the same for everything, so we'll call it I, is equal to voltage, of course. That's Ohm's law. It'll be true in any scenario, as long as you know you're comparing the right things. Obviously, if I compare R1 and I1 to this V, it won't be correct because we're not comparing the same thing. But if we compare this V here to this entire circuit, where the rest of the circuit is using I, because it's the same I, of course, and RE, which is the equivalent resistance of the entire circuit, then you'll get the right value. You get the right equation. And as we use here with loop rule, V equals V1 plus V2. And then we can see from this equation, let's manipulate it a little bit. So let's say that we get, let's say we get V1 is equal to R1 over R2 times V2. And we can plug it in to here, this equation, plug it in, we get V2 times R1 over R2. Oops, that's pretty badly written. Plus V2. We can just expand this a little bit. So V2, or I should say distribute it, factor it at LIS, is equal to R2, R1 plus R2. So now we have this. And what we can do here is, rather than keeping this R2 inside the parentheses here, we can actually move it out a bit. So we can see V2 for R2 times R1 plus R2 is equal to all this. And what would V2 over R2 be? Well, according to Ohm's law, remember that I equals V1, or I equals V over R. So we can replace that just with I2. And what's I2? Of course, it's just I, because it's all in series. So now dividing by I here and here, looking all the way across, we can see that RE is simply equal to R1 plus R2. And that's the end of our derivation. So we have proven that the equivalent resistance of two resistors in series is simply their sum. So that's a lot simpler than what we did before with the parallel resistors, but both are pretty necessary to understand any kind of circuit. Any questions for this derivation? All right, I will assume that's a no, so I'll clear it all. And here's a quick practice problem. So you guys can whip out some paper, figure out how to solve this. Maybe you can do it in your head if you're good enough, but I'd recommend trying to use a paper and drawing it out, figuring out the equations using the rules that we had before. I'll write it down over here. So R for resistors in series, S for series is equal to R1 plus R2. R for parallel, our equation was 1 over R parallel. I'll write that a bit bigger. So 1 over R for parallel is 1 over R1 plus 1 over R2. And if you look here at this diagram, you can see that all three of these share the same branch. They have the wires going through all three of them. So you can probably envision that we'll be using RS, R series for this kind of problem. So let's figure it out. I'll give you guys a couple minutes to do that. Oops. Also, if you solve it, just throw your idea in chat. You can DM it to me, or you can put it in the open chat where everyone can see. You can say it out loud, whatever. All right, that might be enough time. Maybe you guys are still working on it, but I'll just start working on the board, and you guys can compare your solutions to what I'm doing. So what we have here is basically we want to find the current through each component and the voltage across each of them. So first off, right off the bat, we can see we have total voltage, and we have the resistance for each of them. So that's quite a lot of information, and we can figure out right here that the total resistance of this entire branch right here, and therefore the entire circuit, is going to be 60. Why is it 60? Because 10 plus 20 plus 30 is 60. And because it's in series, we can use this rule of R1 plus R2 is RS. And this is a pretty symmetric equation. So it doesn't really matter what order we go in. As long as we just add up, let's say, RA and RB together, then RA and RB is 30 ohms. And then we can add R, let's say, RA plus B. That's going to be equal to 30 ohms. And then we can add that with the RC is 30 ohms. So we can say RA plus B plus C, also known as just R equivalent of the entire circuit, is going to be 60 ohms. And of course, we could have just done this in one shot, just because similar to how this equation works, we can also just add on an R3 or an R4 and everything like that. So I did a derivation for just 2R, but you can actually do it for more than 2, and you can do it actually for any number of them, and you can show it not too difficultly, just using this kind of same equation to show that this is true for any number of resistors. And likewise, you can show that this is also true for any number of resistors. So just tack those on there as well. And yeah, so that's our quick little equation that we use to find that R is going to be equal to 60 for the total. So RE equals 60. We'll write that down there. 60 ohms. And now, well, we want to find the current through each component. Well, this is all going to be one series. It's all one branch. So that means that current should be the same throughout all of them. So if we just use Ohm's law again, very powerful tool, we can see I is equal to V over R. In this case, what's V? Oops. What's V? Just to 12 volts, because we're comparing the entire circuit here, right? So V is 12, R is 60, so I is 1 over 5, which is also equal to 0.2 amps. So the current through each of these components is just 0.2 amps. Now we want to know the voltage across each of them. So the voltage across any of them is just going to be, we can use Ohm's law again, this equation right here, and we can manipulate it to show that V equals IR, right? Some simple algebraic manipulation, and that tells us V equals IR, of course. And the voltage across each of them, we can say VA is IA times RA, right? And then what's VA? What we're trying to find, IA, is just going to be I for all of them because they're all the same branch. So this is going to be equal to 0.2 times what's RA? Well, it's right here, given to us right here. So times 10 is equal to 2 unit for voltage is volts. So 2 volts for VA. And similarly, I'm not going to write out everything, but VB is going to be equal to 2 times that, so 4 volts. VC is going to be 3 times VA, which is just going to be 6 volts. And you can see here, 2 plus 4 plus 6 does indeed, in fact, equal to 12, which means that loop rule here is followed along with it, in accordance with that. So basically, a quick sanity check, you can always just go back and check, like, hey, does loop rule make sense here? Does junction rule make sense here for equations that use junction rule, or things that have a junction rule like that? And yeah, you can always just use that quick sanity check just to make sure you're not royally screwing something up. For instance, if I found that I was 0.3 instead of 0.2, let's say I just had a brain fart, forgot that 1/5 doesn't equal 0.3, or let's say I thought 0.3 equals to 12 over 60, some kind of calculation mistake like that can very easily go overlooked, especially if you're having a long problem. If you have a big equation you have to solve, algebra mistakes are very easy to make. So hopefully you'll make it on the first try. But if you do, you can always just go back and check that everything makes sense. Because if I use 0.3 here, let's say this was 0.3, I would have gotten 3 volts, and then I would have gotten 6 volts, then I would have gotten 9. So 3, 6, and 9. If I add them all up, I would get 18 volts. And that doesn't make sense, right? Because that'd be 18 volts over here, 12 volts over here. That wouldn't satisfy loop rule. So just a quick sanity checks can help and go a long way, especially if you're on a test or a competition and you really need those points. It really makes a big difference on whether or not you can make sure that your answers are actually correct and make sense or not. So are there any questions with that? If there aren't any, that'll be it for today because it's already 7. All right, looks like there are not any questions. So thank you. You're very welcome. And I will see you guys later. So thank you for coming. Great teaching you guys. Goodbye.